this video, I'm going to tell you about the unions, intersections, differences, and complements of sets. So far we've talked about basically what a set is, what a subset is, and even one particular way to try to show that one set is a subset of another set. One way to do that. So in this video, again, we're going to talk about what are like some new sets I can make out of old sets. So let's start with the definition. So the first thing I'm going to tell you, so for all the things I'm going to tell you about in the next couple minutes, let's fix two sets A and B. The first thing, the union of A and B is the following set. So it's denoted with like a big U between them, A union B. And how should you read this? I'm trying to say it's the set of all things X, such that X is an element of A, or X is an element of B. And how you should always read OR, unless otherwise stated in math class anyway, is OR is not exclusive. So OR includes possibility that X is in both A and B. That's cool. A little picture over to the side, like a Venn diagram. So I've shaded the union of A with B, and we're kind of just mashing A and B together. Another word for the union sometimes might be join, I think, in computer science language. Number two, what's another thing that we can do with two sets? So we could take the intersection of A and B, and it's the following set. So the common notation for the intersection is like an arch between them, or some of my students call it an upside down U. But what is it? It's all elements X such that X is an element of A and X is an element of B. So that word and there is important. So you should understand that and is different from or. They tell you different things. So you should treat and both as synonyms of each other. So the intersection is all the things that are in both sets A and B. So it's kind of the overlap of the two. And I'm trying to illustrate what I mean by overlap, again, with a Venn diagram. So the intersection is that shaded region in the middle. Now the third thing that you might not have heard of before are the set differences. And I've got two differences that I'll define. And the notation that I'm going to use is just like a slash, like a backslash. And so and I'm going to say that though as A minus B. Some books actually use like a minus sign, like a hyphen between them, and that's fine too. So I'm just using the slash though. So what is the set difference A minus B? It's the set of all things X such that X is an element of A, but X is not an element of B. And I've got a little picture with my Venn diagram. We're just talking about all the things that are in A but not in B. And if I do the other way, the set difference of B and A, or in other words, B minus A, is going to be the set of all things that are in B, but not an A. And I've colored that to the side too, just to give you a visual representation of how you should think of it. So these are the things we're going to play with. For the moment, let's make sure that we understand what these things are. So what if I gave you these two sets, 1, 2, 3 is A, and B is the set 2, 3, 4. And what do I want to do? Well, I want to practice taking the union, the intersection, and some set differences just with these two given sets. And so A union B, remember union, that should be all the things that are in either of the sets or both of them. So one way to think about that, how I think of it anyway, I'm just going to make one big set out of the stuff in A and the stuff in B. So I'm just going to throw it all together. So I should just get the numbers 1 through 4 there that I've listed. Remember that when you write sets down, you don't have to repeat elements. And the order that I write them in isn't necessarily important. I just did that to keep track of what's in the sets. So there's the union. And so what you should notice out of this is that A is a subset of the union of A and B, and B is also a subset of the union of A with B. So A union B is a bigger set that contains both the things that are in the union, if that makes sense. The intersection of A with B, so I've got some scratch work to the side. I just kind of like to line up the two sets for a problem like this and think about, okay, intersection means both, right? It has to do with that word and is synonymous with both, so you're just kind of looking for where they overlap. And I've colored 2 and 3 there. So the intersection would be the set that just contains 2 with 3. Now, something you should notice here, the intersection of A with B is a subset of each of the sets A and B. And so the intersection, and you can kind of see that actually in my picture of the intersection up here, that shaded region that's green, that's part of the A circle, so it's a subset of A, and it's part of the B circle, so it's a subset of B. So not telling you anything new, just describing it a little bit differently. Now let's take a look at the set differences. So what is A minus B? Remember, that should be all the stuff that's in A but is not in B. And if I line them up here, it looks like the only thing that's in A that's not also in B is just 1, and I've colored that differently. So you see that the set difference of A with B is 1. And now for number 4, when I just go the other way, what is B minus A? I'm going to do the same work, and so now I'm looking at what are the things that are in B but are not in A, and I see that 4 is the only thing that is in B that is not an element of A. So B minus A is just the set that has 4 in it. Another definition that we've got, so moving away, because maybe that stuff's kind of easy. So if you're given a particular problem or setting, so you're going to do some math problem, and who knows what area of mathematics you find yourself working in, we need to know context. And so the set of all elements in consideration is going to be called the universal set. And what we're going to try to do is just give a few little examples to illustrate when do you have context in a math problem. So for the first one, something that you probably do in like a college algebra class, find all real solutions to this polynomial equation x cubed minus x squared plus x minus 1. And so you're told the key word in there, like what kind of answers do you want? You want real answers. And so this problem is indicating that the universal set would be the real numbers, which remember we denote by a boldface R. Let me tweak that problem. Oh, by the way, sorry. So what does that tell me? When I actually solve the problem, the only answer I would write down is 1. So the solution set is just the set that has 1 in it. And again, if we are to consider that the universal set is the real numbers, then the solution set to that polynomial equation only contains the number 1. Now, if we change that problem slightly, and notice all I've done is I've changed the word real to complex, what changes now? Well, now the universal set are the complex numbers, which we denote, by this boldface C. And now when I think about solving that cubic equation up there, we're going to get 3 answers. We're going to get 1, I, and minus I. So now the solution set, it's not the same as the previous example. And again, I have different context. So the universal set is kind of determining context throughout these problems here. So that illustrates that concept. The last definition I'll tell you about, if you've got a universal set U, and you've got a set that's contained in there, then one other kind of operation that we can do is take the complement of a set. And so the complement of a set A is the following. I'm going to denote it by A with like an exponent of a C. Some other books use a bar. There's a chance that you take like a topology class, and a lot of the time the bar means something else. I think the AAC is pretty common in like a probability class, so I'll keep that. So AC is going to denote the complement here. And what is it? It's the set of all x that are in the universe such that the only requirement is that x is not an element of A. So I've got a little picture on the side there. I've got the universe that I've denoted with a box, and A is the little circle that's inside of there and shaded in. So what I'm saying is the red is the complement of A. And just notice it's all the stuff that's in the universe still, but this does not include the yellow A circle. And so some things to note as far as the complement goes. The complement of A, that's the same thing as the set difference, U minus A. So if you're thinking that connection, yes, you're right, perfect. And the other thing that you notice from the picture, if I take the yellow set union with the red set, you just get back everything in the universe. And that's a rule, that's a law. So the complement of A union with A is the universal set. Maybe another rule I could have written down is notice that the red and the yellow don't have any overlap, so their intersection would be empty. And that has some important, both of those have like applications in probability theory too. All right, so let's just do an example though, because what we're mainly interested in is just, given a universal set and a set, can I find its complement? That's the outlook that we have for this video. So let U be the set A, B, C, and D. And let's just let A be the letters A and B. And the goal is to figure out what the complement of A is. And just the strategy to do that, look at the universal set and just tell me what are the things that are in U that are not in A. And I've tried to make that easy. I see that CD is the stuff that's in the universe that's not in A. And so AC would just be the set CD. Let's do another example that is, maybe a little bit more like, sets that you play with more often in college algebra, say, or calculus. Let's let U be the real numbers, so that's the universal set. And now let's let the rational numbers be A. And if I haven't said this before, you've not seen it before, this boldface Q is typically what we use to denote the rational numbers. And now what do I want to know? What is the complement of the rational numbers? If I know the universal set is the real numbers. And of course, you would tell me, well, the complement of the rationals would be the irrational numbers. So things like square root of 2 and pi and e and all those good numbers are in the complement of A. The last one we'll look at is what if the universal set is the complex numbers? And then what if A now is the set of real numbers? Then what I want to know is what's the complement of the real numbers considered as a subset of the complex numbers. So considering the universal set as the complex numbers. So how are we going to think through this? what you would typically do is you would write down, well, what do the elements that I have at hand look like in general? And, well, they're complex numbers. That's the universal set. So maybe that's what I could write down first. So I know complex numbers look like a plus ib. And again, if you put bi at the end, that's fine. Doesn't matter if you put I in front of b or behind b. So complex numbers, though, they always look like the set of things, they always look like a plus ib, such that a and b are real numbers. And now I want to think about, though, how do I make sure this complex number is not itself a real number? And what do I need to make sure happens? I need to make sure that I is always there. As long as there's an I in the expression, then it can't be a real number. So I'm just going to stipulate that b is not 0. And so this would be the complement of the real numbers in the complex numbers.